Okay, thank you for this invitation and for being here. And sorry for the delay. I was going to the usual room and I discovered that I was wrong. Okay, so the title of my talk is Sequential Averaging Processes. So let me immediately tell you what I mean by that. Yes? Oh, that's great. Which one? Yes. Okay. Okay, that's great, of course. And the pointer is which one?
The upper one.
The upper one. Okay. So here's the thing. I'm interested in this type of, let's call them discrete dynamical systems, where you have a state xn, which lives in some normed states. Okay. And it evolves according to this very simple dynamics. So the next iterate xn plus 1 is just the average of the previous state and a certain yn. The assumptions are very general. Alpha n is a scalar between 0 and 1, which is how much weight you put on the previous state and how much weight you assign to the new observation yn. And yn is a vector in x, which can be either given exogenously by some other process that you do not control, or it could be, well, in particular, this could be either a deterministic sequence that drives the dynamics, or it could be even deterministic plus stochastic term. The yn could also be purely state dependent, so yn is just a function of the previous state, like here, t of xn. And frequently this operator t will be non-extensive, by which I mean these points are mapped to closer than the initial points. Or it could be also state dependent plus a perturbation. Okay? So the whole talk would be on this SAP, sequential averaging process. And, no, down. Okay. So the outline of the talk is as follows. Well, first I would like to convince you that this iteration is meaningful. So I will drive you through a sequence of examples drawn from different areas, which fall in this type of iteration. Again, sorry for that. Okay, should be careful with that. So first, I will try to address why this iteration is interesting. In fact, you can argue that any iteration can be written in this form. So I will only focus on some particular cases which really take this form in a natural way, not an artificial way of transforming this into that. Second question is, well, does the iteration converge? Does the xn go somewhere? And if so, at which speed? How can we measure the speed at which the process converges? Again, the other way around. So the talk will be split into parts. The main part will be part 1, which is essentially examples. And I would try to spend half an hour in examples. So can you tell me when I'm reaching close to half an hour just to skip maybe some examples? And then I will go to the second part, which is specifically concerned with the non-expansive case, which is the one I have worked in. In fact, the examples, some of them I have worked, most of them not. They're drawn from different literatures. So in the second part will be a survey of what is known and a little bit of what we have done. So here's the examples. I have 6 of them, in fact, 6 classes of examples. So the iteration may come just purely as an algorithm to compute fixed point for an operator, or the iteration could come as a discretization of some continuous time process. So I will try to briefly sketch what are the relations between the two, and it can go both ways. you can use the continuous dynamic to analyze the discrete problem, or the other way around. You use the discrete problem to say something about the continuous dynamics. Then I will talk a little bit about convex minimization algorithms, which frequently fall into this category of iterations. Then some more specific applications, one from image restoration, the second one from traffic equilibrium in cities. A fifth problem, which well, I will tell you about. It's funny. There's a funny story about that problem. An application in discrete probability. I thought it was easy. It turned out to be extremely complex and very well studied, in fact. And finally, I will, if I have time, I will go through these stochastic approximation examples, which also can be seen as iterations of the main SAP iteration. Okay, so first set of examples. Consider that we have a map T that maps a certain convex set into itself, which is Lipschitz of parameter rho. So when rho is strictly less than 1, which is a strict contraction, probably you all met somewhere in your undergraduate studies the Banach-Picard iteration, which simply iterates like this. The next iteration is just the image of the previous one. So it's the case where alpha n is equal to 1. You put all the weight on the new. And in that case, we have a lot of, I mean, the analysis is quite simple. You just measure the difference between two consecutive iterates. It is just T of xn minus xn. It turns out that this goes to 0 very fast as a geometric series. So it's convergent. You can have error estimates. You can write stopping rules to decide when should you stop your iteration or approximating a fixed point. Of course, when rho equals 1, this iteration does not work. But quite a few years ago, around the 1950s, Krasnodębski-Mann came up with this very simple iteration. Instead of going the full step to T of xn, just take a simple average between T of xn and xn with weight 1/2. So in this case, alpha n is constant equal 1/2. And it turned out that they were able to prove that even for rho equal 1, so even for non-expansive operators, which are not strict contractions, this iteration converges. But until recently, there were no error estimate, no stopping rule. Recently, I mean the 90s. Okay, so already almost 30 years ago, not very recent. Okay, but these were particular results, and we have made some progress recently. So that's my second part of the talk will be based on that. Okay, what's the relation to dynamical system? Very simple. Take this SAP iteration, take this 1 times xn, put it on the other side, divide by alpha n plus 1, and you can rewrite this in the form xn plus 1 minus xn over alpha n plus 1 equal xn minus tx xn. Then you can interpret this as an Euler discretization scheme for a differential equation. This is what I was telling you. This type of the differential equations are appear very frequently in different domains also. So you can see that there is a two-way path there. You can either use this differential equation as a model for the discrete one and try to infer properties of this iteration from the properties of the continuous dynamics, or the other way around. You use that to prove existence and different properties of the. Okay, so these are, you know, abstract example. Let's go to a specific to develop some intuition. Very simple example. Take the plane, take a rotation in an angle theta. So here the operator is just a linear map which rotates in an angle theta every vector. So you see, if I start from x0, here is theta equal pi over 4. If I just iterate t of x0 and t2 over x0 and so on, I will just turn around. What Krasnodębski-Mann, this iteration, does is that instead of taking the full step to t of x0, it stops at the middle. And then the trajectory you get is this red spiral, discrete spiral, which is an approximation of this blue, which would correspond to the continuous time dynamics. Okay? So that's one simple example to develop some intuition. In particular, I point out that here, it seems that taking 1/2 is the best you can do, right? Eventually, the system will converge to the fixed point of this operator, and the only fixed point is the origin. All the other points are related. So the only fixed point is 0. The iteration does converge to x0 as predicted by the theory. And in fact, if you want to go fast, the best you can do is to stop at the middle, because it's the one which gets you closer to the origin. If I take a step size which is too close to 1 or too close to 0, the convergence will be slowed down. So alpha equal 1/2, the original Riemann iteration seems to be, at least in this case, quite reasonable. We will see that in some sense it is almost optimal, not optimal. That's my last slide. By the way, don't get scared about these 70 slides there. There are at least 10 slides which are just reference at the end, so you only have to resist me for 60 slides. Now, I can stop any point. Okay, here's another cute example. Take a very simple operator. Now I'm working in the space of sequences of real numbers, which are in L1, which are summable. And I focus on these probability distributions on the integers. So sequences that are non-negative and sum up to 1. And I consider this very simple linear operator, which takes a sequence and shifts one position to the right. Okay? Well, this is, of course, an isometry. Okay? Distances are preserved. I'm just adding a 0 at the initial point. So what happens if we apply this iteration starting from this x0, 1, 0, 0, 0? Well, of course, the next iterate will be 1 minus alpha this one, plus alpha 1, the one shifted. So it gives you this, 1 minus alpha 1, and the rest is 0. And now I iterate once again. I have to multiply this by 1 minus alpha 2, and then add to that alpha 2 multiplied by the shift. You get this expression. It starts to get ugly, and so on and so forth. Well, in fact, if you look at what happens here is that at the end stage, what you get is exactly the distribution of a sum of independent Bernoullis, which are non-IID. I mean, it's a sum of Bernoullis where each Bernoulli is of the form alpha I. And the distance from xn to t of xn, in the normal one, it turns out to be twice the maximum, because all these distributions are known to be unimodal. They grow and then they decrease. So if I shift one right, I only have to sum up all the increments, and this gives you, well, there is these increments which go up and then they go down, so you get 2 times the highest point here. I will come back to this example later. So just with this very simple operator, you get something which to deal rather with probabilities, distributions of sum of Bernoullis. And in fact, if you look at the continuous semigroup associated with that, the solution is just a Poisson distribution. So somehow the relations we're establishing within the discrete and continuous in this setting, they give you some relation between, or how to study relations between sum of Bernoullis and Poisson process. Okay? But our approach is not probabilistic, it's purely functionality. So those are 2 examples. Let's go to the second class of example, convex optimization. Suppose that I'm given a smooth function from a Hilbert space, let's say RD, to R, and I will assume that the gradient is Lipschitz with known constant, with L Lipschitz constant. And I will assume, moreover, that the minimum of this function is attained. I would like to have methods to compute that, to find a minimum. Very old idea, gradient flows. Just follow the steepest descent, starting from a point X, moving to the direction of minus the gradient. This is the steepest descent idea that goes back to Cauchy. And that's in continuous time. In discrete time is the standard gradient method with step size lambda n plus 1. Of course, this gradient is just ellipses, it's not contraction. But it turns out that this map, x minus 2 over L gradient of f, is a non-expansive map. And you can rewrite this iteration using this map exactly in this form, as before, with this alpha n, L times lambda n over 2. And of course, we require this less or equal to 1, so that, but this is the standard assumption. When you see all the studies of gradient step for fixed step size or variable step size for Lipschitz map, you usually assume that your step size is smaller than 2 over L. These are the conditions you require for convergence. So it's not a mystery. The results are well known. I am only here pointing out that there is a connection with gradient methods. But of course, this requires a lot on the data. You're requiring f to be smooth, with Lipschitz constant, which is known, and so on. So what do you do if you want to minimize some more complex function? Let's keep still a convex function, but which might contain constraints. So it might take infinite values to represent constraints, and this is just a proper closed convex function. That's a technical detail. For those who don't know, never mind. And given that function, Martinet and Monro, they came out with this idea of regularizing the function f by performing this operation, which is called the POCS operation. So you take the function, you add to it a quadratic term, a quadratic deviation with respect to the current point x, and you minimize over all the space, over the whole space. F is convex. This is strongly convex, so that this optimization problem has a unique solution. Okay? To get some intuition, suppose that f of y is just the indicator function of a convex body. Function which is 0 over a convex and plus infinity elsewhere. Well, this is just the projection of x onto the set. And this is a generalization for convex functions, which need not be of the form of an indicator. And together with this POCS operator, to each x, it assigns the unique optimal solution of that point, of that problem. Together with that, I take the reflection operator, which goes from x and goes twice in the direction of the POCS. So it's defined as twice the POCS minus x. Well, it turns out that these two operators are non-expansive also. Okay? In general. No assumption of Lipschitzianity, smoothness, or anything. It is always, both operators are non-expansive. And the inexact proximal point iteration is like this. You take xn plus 1. Ideally, you would like to take the POCS of xn, except that solving for this is not easy because you have to, in principle, you have to solve already an optimization problem just to find the next iterate. So it's very important to allow for errors in the computation of the map. The map is well defined, but you cannot compute it exactly, so I will compute it up to an error, which I call en plus 1. Yep. Usually, yes. The lambda n's are fixed, but the results are very strong. So essentially, the only thing you require about lambda n is that the sum of lambda n1 minus lambda n is divergent. And that's it. With that, you can ensure that the iterates converge to a minimum. What's the relation with the SAP iteration? Well, you just observe that the POCS is just from here. You can take the POCS as 1/2 x plus 1/2 of the reflection. So in fact, the POCS iteration is just a sub-iteration with a fixed step size alpha n equal 1 over 2. Okay? And this is for fixed lambda n. Okay? Otherwise, the analysis goes much beyond that. But at least in the case of fixed lambda, this is just POCS, again, with an alpha n equal 1 over 2. Well, computing the POCS is not always easy. And in several cases, you have optimization problem where you have to minimize the sum of things. And maybe the POCS of f is easy to compute, the POCS of g is easy to compute, but the POCS of f plus g is difficult. You know, just think of projecting to an intersection of sets. It's usually much more complicated than projecting over one and projecting over the other. Maybe you have two simple sets where the projection is easy to compute, but to project into the intersection could be difficult. So splitting method, they exploit this structure, and they make iterations exactly of this form, where the operator T now is a composition of reflections. Let's say I project onto the first set, then I project onto the second set. This is von Neumann's alternative projection method for the case of trying to find a point in the intersection of two convex sets. More generally, when you have to minimize the sum of things, you can apply this iteration. And when alpha n equal 1, this is known as the Douglas-Ratchford splitting. And when alpha n equal 1/2, it's called the Pisman-Ratchford splitting. They were studied, of course, before independently, let's say, of these SAP iterations. And there is a whole book dealing with this and much more complex iterations. Next example, image processing. So suppose I take a picture, an original image, spot satellite image, and because of the atmosphere, there is some blurring, and moreover, there is some noise. So in fact, what you observe, what you get is this image. This is, of course, artificially cooked. It comes from the book from a paper by Convex and company. So the original image in here is a, let's say, grayscale vector, which goes from a domain, which is the square here. This is the omega. And this image, we have some prior information on what the image is. But we observe just this one, which is, we observe y, which is b times x bar plus u. B is a blurring operator, and u, for instance, could be a convolution operator, which mixes because of optics. And u is just a white noise. And the goal is, from here, try to go back to there. So here's one option, which is called total variation restoration, which first considers all the a priori knowledge we have about the image. For instance, we may know that the image is in grayscale from 0 to 255. This is the real image we are trying to cover. We also know that, you know, from the type of pictures we're taking, we know the average value of gray or black that should be present in the image. So you know the average of X. Or you may know a bound on the total variation of the image. And you can add whatever you want. I mean, you can add constraints on the Fourier transform or many others. So I have a bunch of prior information, and I'm trying to recover the true image, X bar. So I know that X bar should lie in this intersection of sets. And then I just do a mean squared, sort of least square approximation, where I minimize, I take the X such that B times X is the closest to my observation. And also I can add some regularization term to avoid X from being too wild. Okay? So mu and tau are parameters which are estimated from previous image. So for instance, in the previous example, which is a spot 5 satellite image, the domain is discretized into pixels, and in this case, we have a problem in finite dimension. The dimension is 256 times 256. And here's the algorithm, a well-known algorithm that is used frequently in image restoration. What you do is that you consider this non-expansive map. So I take the current point X, I project into each and every of the convex sets I'm expected the image to lie on. And then I average these projections. Of course, each of these maps is non-expansive. The average is also non-expansive. And then what we do is that we take a certain step size, which now is not fixed to 1/2. It depends on the distance from Xn to the sets Ci. So this is a case of endogenous step sizes. And then I take Zn plus 1, the average of Xn, plus alpha n plus 1, this operator. And then this is an intermediate step. And then Xn plus 1 is a minimizer constructed from the Zn. So This is not exactly in the form of SAP iteration, but it's closely related. It uses the idea of averaging in an intermediate step. This is called projection autoconvex sets as an algorithm. It was proposed by Andrews and Hahn in '77. It's been widely used. And if you do that, this is what you get by solving that iteration. And this is what you get. This is the recovery image from that. Pretty good. Okay. How am I doing with time? Time? Almost 30 minutes. So very quickly, traffic flows. I'm trying to predict congestion in a city like Santiago, which I model as a network with nodes, with arcs. I have known travel demands. I know how much people want to go from this origin to that destination. I have the routes that connect this destination. And to model congestion, I assume that every link has a travel time which depends on the flow in an increasing fashion. So every arc has a travel time there, which is an increasing function of WA, which is the total flow on the link. And the question is to discover how, or to model, how this demand from I to D will split among the relevant routes. And the modeling paradigm here is that, well, this splitting should be non-negative, should add up to the demands. And it should be the case that only shortest routes are used. This is the rationality assumption behind the model. Namely that if a route gets some flow, it should be the case that the travel time of that route, TR, should be the best possible for the origin destination ID. Precisely, the travel time of a route is just the sum of the travel time on each of its links, which depends on the flow, but the flow depends on the split. This is just accounting. The total flow on a link A is just the sum of the flows on all the routes that pass through A. Simple accounting. And tau ID is just the optimal travel time given those splitting. That's what you're looking for. You're looking for a split which is consistent with itself, which is optimal with respect to the congestion that it induces. This model has been around. It was proposed by Wardrop in the 50s, if not earlier, by some other guys. But formally, the mathematical model was already studied in '52 by Wardrop. And a lot is known about it. I only want to mention that a very common approach to find an equilibrium is this very simple iteration. You start from a guess of what the flows will be. You look at what are the link travel times induced by that. You compute shortest path by your favorite algorithm, Dijkstra or whatever. And you assign all the demand to that route, to an optimal route. If I do that carelessly, it will not converge. But what they usually do, they compute the resulting flows, and they take as next approximation, Wn plus 1, just the average of the previous one, and then this one. The intuition behind that is that I have a population and only a fraction alpha n plus 1 will move to the shortest path. They do not move all simultaneously, but just a fraction. And in fact, a Wardrop equilibrium is just a fixed point of this map that goes from W to the W tilde, except that in that case, that map is really expansive. And in fact, it's not even single valued because there are multiple. You have to choose one shortest path, and usually there are many. Okay, but the worst thing is that even if it was unique, it's expansive, so that you cannot expect this to converge. But it does. So except that the analysis comes from a completely different. You exploit the fact that there is a potential behind. It's not only a non-expansive operator, but it comes from an optimization problem. Okay. Next, this is the funny example. Suppose I give you an IID sequence of Bernoullis variables, just one half. I flip a coin, and I put Bn equal to 1 or 0, depending on heads or tails. And I give you a constant alpha, and I just iterate, consider this very simple iteration. Xn plus 1 is 1 minus alpha Xn plus alpha Bn. Here, the Bn is exogenous. This is the Yn in the journal framework. Well, of course, all of these values are between 0 and 1, and in fact, it's quite trivial to see that the limit exists, and you get this. Well, these are random variable, n plus 1, and it has a limit distribution, which is this. It's a discounted sum of Bernoullis. So the funny thing is that in a summer school a few years back, there was an open problem session, and I gave this as an example, as an exercise. You were there, I think. I gave this as an example, you know, just to have fun, study this iteration. I had no idea about this. Then I later discovered that it has a long story, which goes much earlier than this. It has application in dynamical system and Hausdorff dimension. Don't ask me exactly the details because it's a while that I read those papers. But in fact, if you go to simulation, this is the picture you get. So depending on the value of alpha, you may get very nice distribution, wild distribution, very wild distribution, and singular distributions. And in fact, this was studied as far as by Whitner in 35, and a lot is known. It's known that the distribution you get in the limit is either continuous or purely singular, no mixed. It is not to be singular for alpha bigger than 1/2. It is not to be uniform for alpha equal 1/2, and continuous for these precise values of alpha, so dyadic, essentially, weights. And then Erdős came in and gave a couple of results. It is known that this distribution is singular, is 1 minus alpha minus 1 is a episode that I cannot read that name. You can read it by yourself. And so on and so forth. Then he proved that for all alpha small is a continuous distribution. And the most recent result I'm aware of is this 95 paper, which showed that for almost every alpha in 0 1/2, the distribution is continuous at an L2 density. So the message here is that behind those SAP iterations, you may have very strange behaviors, especially when the step size is fixed, is constant. So be careful when you try to analyze general iterations with alpha constant, because it may be hiding very strange animals like these ones. Okay, finally, stochastic approximation algorithms. What is that? Well, it's a case where you take not alpha n fixed, but alpha n going to 0. Okay? So what is a Robbins-Monro process? It's a stochastic process which lives in finite dimensions and which obeys this type of recursion. Xn plus 1 minus xn divided by alpha n plus 1. I'm writing in the form of an evolution equation, but of course this can be translated into the SAP iteration. And this increment, or this discrete derivative, evolves according to a fixed field, f of xn, plus a random error. So f is assumed to be Lipschitz, epsilon n, a sequence of random variables in a certain probability space. We assume that it is adapted to a certain filtration, and which is a difference of martingale. So the expected value of the next noise given the past is 0. And of course, the analogy is similar as before. You can interpret that not only as a discretization of this differential equation, but a discretization with some perturbation. Okay? And in fact, the main result one of the main results in this area is that you can infer the behavior of this by looking at this continuous time deterministic dynamics. Essentially, the message is, if these dynamics, they're nice and they converge somewhere, then that Robbins-Monro process will have this exactly the same, will copy exactly the same type of behavior. More precisely, here's the result, which goes back to Robbins-Monro. I will give examples next. So suppose that I have a Robbins-Monro process, which I assume a priori, which lives in a bounded set. And I assume that the noise is bounded in some LP norm, let's say in L2. And then I have to assume something for the step sizes, I impose that the sum of alpha n goes to infinity. You see, alpha n works like a discretization parameter of the time. So sum of alpha n equal infinity mimics the fact that we are studying the differential equation in the limit when time goes to infinity. And second, there is a control on the alpha n's. The alpha n's should not go to infinity too fast. They should be such that it compensates the noise, or it makes the noise vanish asymptotically so that the discrete dynamics mimic closely the continuous dynamic. Under those assumptions, you can prove indeed, it was done by all these people, that almost surely the limit, the omega limit set, so all the set of limits of your trajectory, point-wise, for each omega, or for almost all omega, this will be a compact set which is invariant for the continuous dynamics, and moreover, this set has no proper attractor for these dynamics. This is called internally chain transitive. This is a bit abstract, so let me go to the corollary of that, which tells you the following. If the continuous dynamic has a global attractor, so if all the trajectories go to a certain steady state x star, then the process converges to that steady state with probability 1. And if x star is only a local attractor for the continuous dynamic, then you can ensure at least that you will converge to that with positive probability. Yes. Extend bounded. Yeah, I will give you 3 examples. It's strong. You have to check it independently. Yeah, there are some things along those lines, but there are situations where naturally the iterations stay bounded. Here is one example, which was in fact the motivation which started all this stochastic approximation, was Robbins-Monro in a paper in 51. He was studying this problem. He wanted to estimate the intensity for a radiation therapy to reduce a tumor by a fraction rho in expected value. So you have a treatment, you apply that treatment, and depending on the individual, it will have better or worse behavior. You would like to estimate which is the right intensity of the treatment that allows you to reduce by a factor of rho. So how he went about this problem, he said, okay, the treatment effectivity, let's say that it is a random variable, which follows a certain distribution that depends on the intensity of the therapy, on x. And I will assume that the expected reduction of the tumor is an increasing function of x. The higher the treatment, the bigger the reduction. So I'm assuming that m of x is an increasing function, except that I don't know the distribution f, and I don't know the expected value m of x. So how can we find a solution of this without knowing anything, essentially, with only these qualitative properties? So he said the following. Well, we can make trials with different levels and observe the outcomes. Okay? So I will probe this, I will sample this distribution at different levels, x0, x1, x2. For each new patient, I apply a different intensity. And then I compare the outcome, yn, which I observe, to the desired outcome. If yn is bigger than rho, that means that probably xn was too large. So I will reduce xn plus 1 by xn, I will reduce it by this fraction. The other way around, if yn falls short of rho, it's smaller, then I should increase xn. And we iterate this. Well, if I look at this iteration, the corresponding ODE, you take xn on the other side, you divide by alpha n plus 1, and the ODE is just this very simple one-dimensional differential equation. By the way, here, the state, it's always between 0 and 1 because we're talking about fractions. So boundedness is not an issue. All the variables here are between 0 and 1. The corresponding ODE is this one, which has a nice behavior. It has x star, the solution of that, as the only steady state, and moreover, is a global attractor, so that in fact this process converges almost surely to the solution without knowing anything, except that you're allowed to test or to probe to observe outcomes. I related also from statistics a law of large numbers. Not the most general, but already I think it's interesting to make the connection. Suppose that I have a sequence of IID variables which are bounded. So this is a limitation which comes from that part. Of course, there are law of large numbers which do not require boundedness, but in this case, and suppose that the expected value is mu, and let's take xn, the empirical average of the first n observations. Well, if you look at what xn plus 1 is, it's just a modification of the previous average, a small modification. And in fact, the iteration satisfies xn plus 1 minus xn divided by 1 over n plus 1. So here alpha n is exogenous, but it's going to 0. The sum of alpha n is infinity. The sum of alpha n squared is finite. So all the hypotheses are fine there. And you get this iteration. This difference is just the new iteration minus the previous state. And this yn, I can write it as the average of the distribution minus an error, or plus an error. And then the corresponding ODE to this is even simpler. It's dx over dt equal mu minus x, which is just, has an explicit solution, which is an exponential that goes exponentially fast to the average. And therefore, from the general theorem, you obtain this, law of large numbers very as a particular case. How am I doing with time? I'm over half an hour. Only 15 minutes left. So let me skip this one. This was about adaptive learning in routing games, which is one of my topics of interest. I will skip because it's quite long. And I will go to second step. As we saw, there are several examples, some of them of different natures. And many of them deal with non-expansive maps. All the optimizations examples were for non-expansive maps. The one I just skipped, of learning in transportation is also non-expansive. There are many cases where the iteration is this one. So for the rest of the talk, I have a normed space, I have a closed convex bounded set, and I have a non-expansive map. And the iteration I'm interested in is Krasnoselski-Mann iteration. Xn plus 1 equal the average of the previous, exactly as the SAP iteration for state-dependent Xn. Well, this was introduced by Mann in '53 without proving much. He presented a whole class of positive iterations, more complicated than this. This was contained there. And the first result I know is Krasnoselski, he proved convergence when n equal 1/2. If C is compact and X is a uniformly convex space. This generated a lot of works. It was extended first by Schaeffer to not only to alpha equal 1/2, but to any alpha constant. The space was no longer uniformly convex, but only strictly convex. And Edelstein is, well, Schaeffer considered that case. Edelstein relaxed the convexity. Later, Browder and Petrushin proved that the norm of the fixed point residual goes to 0 in the case of constant alpha, if C is only bounded and C uniformly convex, and so on and so forth. Many results that follow. The common denominator of all these studies, starting from Krasnoselski to Edelstein O'Brien, is that the crucial step in all the proofs was to establish that the residual goes to 0 in norm. And this was given a name. It's known as asymptotic regularity. We say that Km is asymptotically regular if this holds. Why is this useful? Well, it has a lot of consequences. First consequence is that if this goes to 0, then all accumulation points should have residual equal to 0, so they should be fixed points. And this can be used, in fact, to prove the existence of fixed points for very difficult or abstract operators by using algorithms. You use this algorithm, you prove that it converges, and therefore you conclude that there exists a fixed point. This is the celebrated Browder-Gether-Kirk fixed point theorem. Not only that, we know that, and it's easy to prove that, the distance from the iterates and any fixed point is always getting smaller. Therefore, if you have an accumulation point and the distance is decreasing, well, it should go to 0. So in fact, you get convergence of the full sequence. Even if there are many fixed points, this iteration will converge to one of them. And there is a lot of theorems that essentially what they prove, they spend 80% of the paper improving the first assertion, asymptotic regularity, and then they conclude under different assumption, the convergence to a fixed point. And then Bayon and Brook came up with this conjecture. The previous proof was very complicated, exploited the structure of the norm, strict convexity, strong convexity, were very involved. So it came as a very big surprise when Bayon and Brook came up with this conjecture. He claimed that there should exist a universal constant, which is independent of the space, of the operator, of the convex, independent of everything, a constant, such that every Krasnoselski-Man iteration satisfies that the residual is bounded by the diameter of the set multiplied by this constant divided by the square root of alpha I1 minus alpha I. Conjecture. This, of course, implies all the previous results. If true, this gives everything for free, almost for free. And in fact, they proved this theorem. They proved it in 1996 in the special case when the step size is constant, alpha n equal alpha. And amazingly, the constant they found was 1 over the square root of pi. And from this, you can pass to continuous semigroup, and for continuous semigroup, this is the derivative. It decays like 1 over the square root of t. So it's a very precise estimate. You see, if you have that, you can really find how many iterations you require to get a given precision. It's not only that there exists a constant such that the asymptotic behavior is of this form. It gives you the precise estimate of the fixed point residual. C is the domain of the operator. T operates from C to C. It's the set on which you're working on. Okay? T was an operator from C to C. Now, the paper in 1992 is a beautiful paper. It doesn't have any results in it. It has only conjectures and numerical examples and numerical tests and hints on how maybe we could go about proving such and such. There are at least 10 conjectures. One of the conjectures, the basic conjecture, was this one. They didn't prove that, but they were able to prove it. And the proof is very nice, very unexpected. 10 minutes, okay. It is based on a computer-generated recursive bound for xm minus xm. They estimate the distance from xm to xm. We'll give you roughly the idea in the 10 minutes that are left. But they were uneasy about this. We were also uneasy about that. And okay, some implications of this is that it gives you pretty right away rates of convergence. It tells you that this, for alpha constant, this sum of alpha I1 minus alpha I is order n, so you get a 1 over square root of n rate of convergence. Some previous results were known, which were much weaker, like 1 over log. Oops. Help. Okay. So here is an outline of the rest of my talk, which obviously I will go very quickly. But here is a snapshot of what we have proved about this problem. So here's again the conjecture. There exists a universal constant such that this is true. We want to go over the case of alpha k equal alpha, and moreover, we want to have a human-generated proof, not a computer-generated, because it is based on this Zyberberg iteration algorithm, and it gives you a recursion. They call it the 1 meter long formula. It gives you It's based on a computer-generated recursive formula, which is 1 meter long, and you cannot understand anything, what's going on there. But it works. You can check. But it doesn't give you really an understanding of what's going on. Poor referee, yes. So what we proved? Well, we first proved that, in fact, that formula is correct. It also holds for all alpha n, not only constant, and with exactly the same constant. Secondly, with Mario Bravo, we proved that, in fact, the constant 1 over square root of pi is the best you can expect. We found an example which achieves this constant, and therefore, don't waste your time trying to improve that bound of Bayon-Brook. The best constant is 1 over square root of pi, as far as nonlinear maps are concerned. If you take affine maps, or linear maps, then you can get a better bound, slightly better bound. This is 0.56, this is 0.46, where this is weird expression. And in fact, the tight bound is attained by who? By the right shift operator. It has to deal with bounds of Bernoulli probabilities, so bounding the maximum of a sum of Bernoullis. And using that, we can prove that this bound holds for not only for the right shift, but for any affine map. The worst case is the shift, and this constant is tight. You cannot improve that constant for linear maps. And finally, recently, with Mario Bravo and Matías Pavés, a student, we were able to extend this bound, including the case where you have errors. Of course, the right-hand side should include some terms which are related to the errors, okay? And as I told you, with human-generated proofs. So let me just give you I have 5 minutes? Okay. Let me give you a very brief idea of what are the ingredients. I will go very fast on some slides, but I will try to fix the ideas on the main iteration. So I have to prove such a thing. First, I rescale the norm so that the diameter of the set is 1. And I'm trying to bound this residual, which is just xn minus xn plus 1. So the whole game is to find a good bound for xn minus xn plus 1. We don't know how to do that, but we know how to bound xn minus xn for all m and n. So we copy the strategy of Bayon-Brook. So if you recall, the xn is built as an average of the previous iterate and the image of the previous iterate. If you go back, xn minus 1 will be an average of the previous point, xn minus 2, and the image. And you keep going back, and then you can express xn as a certain average of all the previous iterates, with some very precise weights, pi in, which are some sort of probability distribution over the integers. So now what we do is the following. I have xn, which is an average of the previous iterate. Same thing for xn, is another average of the same thing. I have these blue weights that define xm, the red weights define xm. So what we do is that we consider an optimal transport sending this mass to that mass. Okay, so I consider the set of all possible transport plans that transform this blue mass into the red mass. Let's call that z, will be a variable. So I can replace over there the pi am by this, the pi jm by this. It's just conservation. And then you have this expression. Now they're both similar. You can put them together. And now we use just triangle inequalities. We bound this by the sum of that. Now suppose for a second that I have a bound on the previous iterates. So I have a bound for the distance between di minus 1 and dj minus 1. Let's call that di minus 1, j minus 1. So to build a new bound for the new iterates, for xn minus xn, I only need to have the bounds for previous iterates, and then I can play with z as I wish. And I wish the bound to be as tight as possible so that I minimize over z. And I get this recursive optimal transportation problem, which define inductively this dmn is the minimum over z of that. Well, to analyze that, it seems impossible. Well, first observation, we proved that those bounds are tight. There exists a map which attains dmn, which attains the equality here. So this is the best bound you can ever hope for. Except that analyzing the behavior of that recursion, it may be quite difficult. Notice that we reduced the whole problem to analyze this double recursion. DMN are just real numbers, and MN are sequences. Okay, so everything it boils down to studying these terms. Functional analysis is over. So I don't need any more. So this works for any operator. So the restatement of Bayon-Brook is, well, can we prove that? No, that we know. And the question is, how do we compute Dn n plus 1? Or at least, can we prove that this value, which is over there, is smaller than what Bayon-Brook anticipated? Well, what we do, and here we'll go very quickly, instead of focusing on DMN, we build an upper bound. The upper bound is by considering not an optimal transport, but a feasible transport, which is not that bad. Okay, which essentially moves things proportionally. And with that, we get an upper bound which satisfies recursion, which is simpler. There are no longer optimization problems here. It's just a recursion. And it turns out that this recursion has a probabilistic interpretation, as a race between, you see, there is a coyote who's trying to catch the roadrunner. The coyote is standing at position N, the roadrunner at position M. Coyote starts and he jumps these volts. He succeeds with probability 1 minus alpha k, and he fails with probability alpha k. So the probability that he falls at the jth iteration is exactly those weights that appear in the expansion of, okay? So the coyote starts. If he jumps up to position M or below, that's it. The game is finished. The roadrunner was captured. Otherwise, if he falls in between, he moves, trying to get to -1. At -1, the position is safe. Okay? But he might fall before that, and then it's the turn. They alternate. They play in turns, and they alternate. Now, I ask you, what is the probability that, following this process, the roadrunner escapes? Well, it turns out that this probability satisfies exactly this iteration. Okay? So that gives you a way to compute CNN in an alternative way. You say, well, for the roadrunner to escape, the coyote must fall more frequently than the roadrunner. And then you apply tools from probability now to analyze the recursion. We go to probability. The random walk, gambler's ruin appear naturally in this context. And then by analyzing, so maybe one step back. So what is nice is that we get an exact expression of this term Cn n plus 1. It's the expected value of a function f, which is very precise, which has to deal with the standard random walk, and then an expectation of some sum of Bernoullis with these weights. And then you analyze that, you prove that everything is bounded by 1, and therefore, both cases combined, you have to differentiate a couple of cases. And in fact, you get what you wanted, you get the proof. And now there is a little more understanding of where the 1 square root of pi comes. It comes precisely from these bounds, from these bounds that you get here, which have to deal with these hypergeometric functions in one case, and the second case is dominated by these Bessel functions, which satisfy this inequality, which are dominated by 1 over square root of pi. So that's where the square root of pi comes from. And okay, this I already said. In the affine case, we can do better. That's for the errors. We were able to prove that the 1 over square root of pi is the best possible. And I think I will stop here. And thank you very much.